Hi everyone, Robert J. McKeown here, and welcome to another ALEK's walkthrough video. This one is number 6, and we're going to look at rational expressions, which I think are a very intelligent, smart sounding kind of expression. Now, the specific, what a rational expression is, I'll tell you in a few moments when we get into the slides. As an economist, we're often trying to rearrange an expression to get a certain result or to solve for an unknown variable. Like, for example, we might want to solve for the price of a product like gasoline or smartphones or software products. Or we might want to solve for quantities produced of similar items. And so it's really, really difficult to get away and not use mathematics in economics. And I really like today's topic because it gets into the real nitty-gritty of what you're going to be doing as an economics undergraduate major. You're going to be rearranging expressions. You're going to be trying to show certain results. And that's what today's practice is all about. So becoming a master of this topic is going to pay off for you in every one of your core economics classes from here to the end of your undergraduate career and then into grad school as well. And being good with math is a great job skill, a very employable skill to have. Now, again, what do I need from you? I need you to have your pencil, I need you to have your paper, or if you're very sophisticated and you have the money, invest in a tablet that you can write and work through the problems with me for this topic and through this video. Remember that the video doesn't cover every important topic in ALEK's Topic 6 or every concept in Topic 6. I'm just trying to get you enough information to make sure that you get started and help you through maybe some of the more difficult problems. So let's get started. Topic 6 is all about rational expressions. So what is a rational expression? Well, it's when one polynomial, such as x plus 5, is divided by another polynomial, such as x squared minus 9. And remember, we've seen a lot of quadratic equations, quadratic expressions are also a type of polynomial. Now, every question in this section involves rational expressions. To start off, why don't we talk about the domain of a rational expression? So in an earlier topic, I told you that we must never, ever, ever divide by 0. And if you look here, it says the domain of any rational expression is all real numbers except for those that make the denominator equal to 0. Now, why is this important? Let me show you an example here. We have x plus 5 divided by x squared minus 9. I can rewrite that using the difference of squares. Whenever I see something squared minus something else that's squared, I can use the difference of squares. For example, I'll rewrite this as x squared minus 3 squared. Right? 3 squared is equal to 9. So I'm going to write this as 3 squared. I know from this rule that x plus 5 is divided by x minus 3 multiplied by x plus 3. And you can prove to yourself at home that x minus 3 times x plus 3 is equal to x squared minus 3 squared, or x squared minus 9. Now, we know that all real numbers are in the domain except for those real numbers that make the denominator equal to 0. So using this right here, it's easy to see that if x is equal to 3, then we have 3 plus 5 divided by 3 minus 3 multiplied by 3 plus 3, which is 8 over 0 over 6, which is equal to 8 over 0. And I told you that we should never divide by 0 because we never observe a real number like 8 divided by 0, so we just don't really know what that is. And so we say it's undefined. We don't know what it is. We can't define what 8 divided by 0 is. Similarly, if x is equal to -3, what happens? Well, we get -3 plus 5 over -3 minus 3 times -3 plus 3. And this time we get -2, or excuse me, 2 over 0. So both x is equal to 3 and x equal -3 are not in the domain. Here's a ALEK's question, and I've copied and pasted from ALEK's, and it tells us that find all the values of x that are not in the domain of G. So I can take a look at this thing here. I can do some factoring. So for these questions, the numerator never matters. It doesn't influence the domain. But I could look at this and I could say, well, I notice that 8 times 9 is equal to 72, and -8 minus 9 is equal to 17. And when I recognize that, I can factor the numerator as so. Looking at the denominator, I see my favorite x squared minus 2 squared is my difference of squares. A very useful formula. It comes up a number of times, including finance. And I can write this as x plus 2 and x minus 2. Now, I didn't need to do that. You could probably just look at the original expression and answer this question. But you'll see later questions we need to be able to do these operations, so I'm going to show you now. And it's pretty obvious here that x equals 2 and x equals -2 are not in the domain. Because when x is equal to 2 or x is equal to -2, the denominator is 0. Here we are on ALEK's. I'm going to put in our answers. We had -2, and then I'm going to follow the instructions. Put in a comma and a 2, and I'll click on the check button, and fortunately we got the right answer. Here's a great question. We have a complex fraction and a rational expression, but a complex fraction. And when I see a problem like this, I want to start off as my first step to find a lowest common denominator for the numerator. And then I want to do the same thing for the denominator. And after I do that, I'll think about what my next steps are. I don't like to see non-common denominators. So that's something that I like to jump on and fix right away. So starting with the numerator, I've got x squared on one side and 49 on the other. So for this first term, 8 over 49, I'm going to multiply it by x squared over x squared. Or I'm going to multiply both the numerator and denominator by x squared. That way I'm following the rules of algebra. X squared divided by x squared is just equal to 1. I'm not changing the expression in any way when I do this. That's the whole idea behind lowest common denominator. Now, looking at the second term in the numerator, I need a 49. I'm going to multiply the top by 49 and the bottom by 49. And now I've got a common denominator. I could rewrite that as x squared minus 49 all over 49x squared. Now, what about the denominator? Let's take a look at the denominator. 1 over 7. Well, I can just multiply that by x. So I'm going to have x over 7x plus, well, 1 over x, I can multiply the numerator by 7 and the denominator by 7. And now I've got x plus 7 divided by 7x. Now, what's the rule when we're dividing two fractions? Well, the rule of the operator is to flip the denominator's numerator and denominator and then multiply it by the numerator, what's at the top. So I can rewrite this as 8x squared minus 49 multiplied by, well, maybe I'll write it out like this. I'll just rewrite it like that. And this whole thing is going to be multiplied by 7x over x plus 7. That's the rule. We saw that in an earlier video. That's how we deal with division. I like the way that I've written it here. I can clearly see what's being multiplied and what's being divided. And I want to pay particular attention to the division, because the division is going to, well, we say cancel things out. I can make a simplification here, and I can rewrite this expression as 8x squared minus 49 over 7x squared multiplied by 7x over x plus 7. And we can cancel out 7x divided by 7x, and I'm going to be left with 8x squared minus 49 over 7x, x plus 7. So it was this exponent that was canceled out previously, not all the 7x's. I went ahead and I input our answer into ALEKS, and you can see that it was the simplest form possible. There wasn't anything more we could really do. There's a 49 there, which is 7 squared, but if we rewrote it that way, we can't simplify any further, because that 8, the 8 in front of the x squared, is stopping us from doing any more factoring. Our next problem is asking us to solve for w. So we've got a rational expression, and there's 3 separate terms. Like before, I want to get started by finding a lowest common denominator. So notice that if I call that A and I call that B, A is equal to 2B's. So if I multiply the numerator and denominator of this term here by 2, they'll have the same denominator, and I won't be altering the value of that term. I'll just fill this in so you can see 2w minus 12. Now I've got this -1 term here. Well, if I want to give it the same denominator as the other two terms, 2w minus 12, I can multiply it. and its numerator denominator, because of course negative 1 is equal to negative 1 over 1, I can multiply its numerator and denominator by 2w minus 12. So if I do that, I'm going to get (2w minus 12 over 2w minus 12), and you can see very clearly that that's got to be equal to 1. And I don't want to forget my negative sign in front. The last term on the left is unchanged. It's still 3 over 2w minus 12. There's a big minus right there. Now, the great part is, since the denominator of every single term is the same, I could multiply both sides of this equation by 2w minus 12. And if I multiply both sides of this equation by 2w minus 12, I'm going to be left with negative 3 minus 2w minus 12 is equal to 14. And you want to be really careful that you don't make a mistake with your signs. Very, very easy mistake to make, one that I make fairly regularly. Not unusual that I would forget a sign here or there. Given that reality in which I operate, I'm very careful to keep my sign negative on the outside of this bracket, because now I want to bring that negative into the bracket, so I'm going to rewrite this as minus 3 minus 2w plus 12 is equal to 14. Now notice that I've just got a w and a bunch of numbers, and so this is now linear. It's a linear equation or a linear expression, and that means I'm going to get one solution. Now I made a small mistake. I forgot a negative sign. I forgot this negative sign, partly because I didn't draw it clearly. I should have a negative 14 there. Now I want to finish this off and solve for w. So I'm going to have negative 2w is equal to negative 14 minus 12 plus 3. And I get w is equal to 23 over 2.